Hello, everyone. This is the second part on infinite limits. On this part, we'll be diving into functions that are has more complexity, which are composite functions or product of functions. And some of these functions include a natural log and the sine function, cosine function, tangent, and cotangent. Okay, so we're going to take this opportunity to review these questions. Okay, let's take a look. And these two limits may still be useful. Okay, these two limits may still be useful. Okay, all right, so let's look at number 5. Let's look at number 5. This number 5 is a composition of natural logarithm and x squared minus 9. Okay, and x squared minus 9. So to see the tendency, you will see that as x approaching 3 from larger than 3, x squared minus 9 is going to be approaching 0 from larger than 0. Okay, so let's first see that. So input, which is x, okay, and output is x squared minus 9. X squared minus 9, okay? So if I choose input as 3.01 and x squared minus 9, right? So x squared minus 9 will be closer, will be a number, okay? So now if I choose 3.001 and the number is even closer to 0 but larger than 0, okay? So as I choose number 3, which is getting closer and closer yet to 3 from larger than 3, and we get numbers, the x squared minus 9 getting closer and closer to 0. Okay, so let's see, 3.00001, and the output for x squared minus 9 is getting even smaller. Even closer to 0. So that process, okay, as you can see, right, the input is getting closer and closer to 3 from larger than 3. Okay, from larger than 3. And the output is getting closer and closer to 0 from larger than 0. You can see all of these x squared minus 9, they're getting closer and closer to 0, but yet larger than 0. So that's 0 plus, right? You can see that tendency. So with that on our mind, so we're gonna write as x approaching 3 from larger than 3, x squared minus 9 is getting closer and closer to 0, but from larger than 0. Now I'm going to deal with natural log, ln x. For those of you who may or may not be familiar with ln x is a kind of function that has a following graph. On this graph, okay, so let me adjust the view a little bit. Make it the other side, make it 9. And this will make it -2, -2, and maybe this side just 1. Okay, that should be sufficient. Hold on. Maybe I'll make it a bit larger. Okay, 5. All right, so that seemed to be 3 will be better. Okay, so I want to give you a good view of it. Okay, this is ln x. This is ln x. From this picture, what does it tell? The domain of ln x is x larger than 0. So we cannot take any value that's 0 or smaller for input of ln x. And also from the graph, you can see as the input getting closer and closer to 0, the output, this is output. If the blue is there, if the input is even closer to 0, the output will be even lower. Okay? If the input is getting closer to 0 yet, and the output will be as close to, it's even lower. Okay? So this is the so-called approaching negative infinity. Okay? Numerically, I'm going to show you some numerical. Let me see. I think probably Excel worksheet can do that for us. Okay. So as the input getting closer to 0, right? As the input getting closer and closer to 0, suppose I'm using these numbers. I'm using these numbers for ln, right? I'm using these numbers for ln. Make it just a little bit smaller. Okay. So that should work. And the next column we're going to make. Okay, the next column we're going to make. So as x approaching 3, as close to 3 as possible, we're approaching 3 from larger than 3. X squared minus 9 is approaching 0 from larger than 0. Okay, so let me just move that. I'm just going to move that. Okay, so this is going to be approaching 0 from larger than 0. If we do the ln, if we do the natural log of x squared minus 9, okay, so that's going to be ln log. So we have an ln, right? So ln, the input is from here. Okay, you can see it's getting smaller and smaller, negative. Okay, getting smaller, negative. You guys see that? Okay, so it's getting smaller and smaller. If I keep doing that, that's 3.0000, many more zeros, and x squared minus 9 is going to be like that, and the output is getting closer and closer to negative infinity. So this is getting closer and closer to negative infinity. Okay. So that process, but you see three processes going on. The input is getting, closer and closer to 3 from larger than 3. And there's an intermediary, which is x squared minus 9. It's getting closer and closer to 0. And ln of that, so that is simulated into the blue is approaching 0 as close as possible. Then the red is approaching negative infinity. Okay, negative infinity. You guys see that? Okay. So as a result, as a result to describe all of these processes. Okay, so as x approaching 3 from larger than 3, the infinite limit will be negative infinity. That will be the negative infinity. So these are the processes that's going on. Okay, so now let's look at the next one, but this requires you to have certain familiarity with natural log x, okay, natural log. And this is a very important function, okay, you will need that for both calculus 1 and calculus 3. And I have lessons and I will send it, I will send it your way. I think I probably have sent it your way, okay? Ask me about it if you haven't received it. So let's look at number 6. Okay, let's look at number 6. Number 6 is a process that certainly we cannot reduce and we cannot do direct substitution. Why we cannot do direct substitution? Because we know sine x, right? Sine x is defined everywhere. It's all real numbers. Sine 0 is 0, but ln 0 is undefined. Ln 0 is undefined because we have reviewed that the domain for ln x, that the input must be positive. It cannot be 0. It cannot be 0. Therefore, okay, so we're going to see this process. So this process requires us to know a little bit about sine x. Okay, if you know sine x from its graph, its curve. Okay, if you know this curve, so from this picture, right, we can see as x approaching 0 from larger than 0 on the sine curve. What does that mean? It means x is approaching 0, right, from larger than 0. Okay, it's a blue. Approaching 0 from larger than 0. And the output are above. So the output are what? A positive, right? So we can see as we approaching 0 from larger than 0, the sign is getting closer and closer to 0, but they are all larger than 0, right? So you see that process. So then we can say as x is getting closer and closer to 0, sine x is getting closer and closer to 0, but from larger than 0. Okay, from larger than 0. And as the sine x approaching 0 from larger than 0, ln x, right? We're approaching ln x, that's going to be approaching negative infinity. So what we analyzed, right? So when this input is approaching 0 from larger than 0, or that is approaching 0 from large. So this whole thing is approaching 0 from larger than 0. If we evoke the curve for ln x, and you will see ln, let's call it ln bologna. Okay, so let me find a symbol for bologna. Right, so this is my bologna. The bologna is assume the position of sine x. Okay, bologna is for sine x. So when x is approaching 0 from larger than 0, bologna is approaching 0 from larger than 0. Therefore, ln bologna is going to have an infinite limit of negative infinity. Okay, so there are two process is a composite function situation that is going on here. Okay. All right. So let's look at number 7. Let's look at number 7. For number 7, we have two functions in this process. Okay, so let me clean this up. We have two functions. One is 1 over x, right? 1 over x, and one is a secant x. So for those of you, if you're not familiar with secant x, No big deal. You could use the relationship for secant x, which is 1 over cosine x. Okay, 1 over cosine x is secant x. Okay, as x approaching pi over 2 from larger than pi over 2. Let me double check if I copy the question correctly. Right here, that's right. Okay, if x is approaching pi over 2 from larger than pi over 2, what will happen to 1 over x? 1 over x is going to be approaching a finite number. Okay, so this is going to be approaching a finite number, which is going to be 2 over pi. Okay, 2 over pi, no matter what the value it is, pi is a constant, 2 over pi is a constant. So that part is a constant. We don't have any issue in the dynamic process when x approaching pi over 2 from larger than pi over 2. Cosine x, however, right, as x approaching pi over 2 from larger than pi over 2, what will be the behavior of cosine? Okay, so we're going to use the curve for cosine curve. We're going to use the cosine curve. Okay, on the cosine curve, okay, we need to identify the point which is pi over 2. Okay, we're going to identify the point which is pi over 2. So I'm going to plot that point for you. Let's pi over 2, comma, 0. So I'm going to get this point graphed on the picture. So right here. Okay, so this point is pi over 2. Okay, we are approaching pi over 2 from larger than pi over 2. Okay, so let me mark pi over 2. Okay, let me use blue color because pi over 2 is the input. Okay, so this is a pi over 2. This number is pi over 2. And the input, okay, is approaching pi over 2 from larger than pi over 2. And what will be the output? The output you can see is getting closer and closer to 0. You see the red is getting closer and closer to 0, but all these red are beneath x-axis, so they are negative. So now we can say, okay, cosine x, because this is a cosine curve, is approaching 0 from smaller than 0. Okay, so that's a constant. And this piece is approaching 0 from smaller than 0 in this case. So treat this as a constant. And this piece is approaching 0 from smaller than 0. So using that form, using this form. Okay, so let me put it here. Using this process, it will be similar. It will be similar. Similar to this, right? Similar to that. Okay? Constant, 1 over a quantity that's getting closer and closer to 0 from smaller than 0. Therefore, this is going to be negative infinity. Right? So what you notice is that these basic process here can be viewed as a simplified version of the process we consider. Okay? All right? So that completes number 7. That completes number 7. So that's what you could, think of in that process. Okay, so let's look at number 8. Number 8. Okay. Number 8 is when x approaching pi from larger than pi. Let me just double check if they right. If I copy the question correctly, I did. If you don't remember cotangent curve, no problem. Okay, we can use cosine over sine to replace. Okay, we can use cosine over sine to replace it. So cosine x over sine x. So what we know is as x approaching pi, right? As x approaching pi from larger than pi, sine x is approaching 0. But whether it's from larger than 0 or smaller than 0, we need to figure that out. So we're gonna bring our sine curve with us. So this is our sine curve. So we bring out the sine curve with us. And we want to figure out, right? When x approaching pi from larger than pi, sine x approaching from 0 from which side, right? So first we need to identify where's that pi, right? So we're gonna get to that point, right? Pi, comma 0. I'm gonna use that dot. So this time I'm gonna use a blue dot for change. Okay, so that's pi. That's pi. So when we're approaching pi from what? From larger than pi. Okay, we're approaching pi from larger than pi. Right? We're approaching pi from larger than pi. I'll make it a little thicker, right? Should I make it a little thicker? So we're approaching pi from larger than pi. And the output, okay, is approaching 0, right? It's approaching, you see the red is getting closer and closer to 0, right? So when x is approaching pi from larger than pi, sine x is approaching 0 from smaller than 0. So I'm going to write it as with a negative sign on the shoulder. Okay? The denominator approaching 0 from smaller than 0. What happened to the numerator? Cosine x, however, as x approaching pi, okay, is going to be approaching -1. Okay, it's going to be approaching -1. So the numerator is negative, which is for cosine x. Sine is approaching 0 from smaller than 0, so it's a negative divided by negative, right? So the whole thing is going to be positive. And which model would be relevant? The relevant model would be this guy. The relevant model would be this guy. Therefore, this is going to be approaching positive infinity. Right? So we use mathematical principle number 6. Mathematical principle number 6. Right? So we have some basic knowledge of these trig functions. You don't have to remember all, 6 trig functions. You already have to just need to know 1, 2, 3, sine, cosine, tangent. Okay? Tangent, yes. Even tangent, sometimes it can be substituted by sine over cosine. Okay, but sometimes we do use tangent directly. Okay, so that was number 8. So let me clean this up. Okay, what we're going to work on, we're going to move on to number 10 because we did number 9 previously. So I'm going to bring this down. You see, from time to time, we need that. We still need that model. These 2 models are just absolutely useful because a lot of situation is condensed or it's simplified to that version. okay? So now what do we have is number 10. Number 10, we have x approaching 2 pi from larger than 2 pi, okay? 2 pi. Number 10, no, from smaller. Oh, okay. I think I made a copy error. It's negative. Did I do that right? Number 10, the 2 pi from smaller, okay? Sorry about that. Since we may not be familiar with the cosecant, no problem. We can use the replacement for cosecant, which is going to be 1 over sine x. Okay, so we can bring this x to the top. So x over sine x. Okay. When x approaching 2 pi, sine 2 pi is going to be approaching 0. We just have to figure out, like, is approaching 0 from larger or smaller? Numerator x is going to be approaching a constant, which is 2 pi, right? So let's bring our sine function with us again, right? So right here. But this time we need to mark 2 pi, right? So this time we're going to mark 2 pi. So this is going to be 2 pi. 2 pi is right there. So our picture needs to be adjusted. So I'm going to make a -1 here. Maybe this is 8. Okay. So that's 2 pi. That point is 2 pi. Okay. So when we are approaching, right, 2 pi from smaller than 2 pi. And what happened to be the output? The output is going to be approaching 0 from smaller than 0. You can see all these red are getting closer and closer to 0, but smaller than 0. So now to summarize that, we can say, okay, when x approaching 2 pi from smaller than 2 pi, sine x is approaching 0 from smaller than 0. So denominator approaching 0 from smaller than 0. What happened to x? Well, x approaching 2 pi. So the numerator is a constant number. Denominator is a number that approaches negative 0 from smaller than 0. And we can use one of these, right? Which one applies? The one that applies is the latter one. So therefore, this piece is going to be negative infinity. I hope that helps, right? Because sine x, you can tell sine x is going to be approaching 0 from smaller than 0. And then our basic form now is comparable in our situation. Okay? So that was number 10. Okay, so let's move on to number 11. Okay, so I'm still going to bring this with us. You can see these two basic models are very, very useful. Very, very useful. Okay, so this time we got a tangent. If you know the tangent curve itself, it's pretty straightforward. Okay, if you don't know the tangent curve, then you can use sine over cosine. So the way to analyze it is similar. So we have done that. So this time we use tangent curve directly. So I'm going to graph tangent x. And from tangent x, okay? And we know that there's a vertical asymptotes, right? So the point of interest for input is pi over 2. So we're going to graph that vertical asymptote, okay? That's pi over 2. Pi over 2. So I'm going to draw that pi over 2 as a vertical asymptote. which color? Let me use the green. Green is not actually, red is probably more reflective of the nature. Okay, so now, oh, sorry, there should be broken line. I want it to be a broken line. Broken. Okay, broken line means the curve cannot cross it. Okay, so where is pi over 2? So we're going to mark pi over 2. Okay, so that point of pi over 2, mark that point on your picture and make it a red dot. Pi over 2. So if we use tangent function directly, right? So when we observe the picture, right? When we observe the picture, we are approaching pi over 2 from smaller than pi over 2. Am I right? Hold on, let me double check, okay? 11, yes, okay, we're good, okay. So we are approaching pi over 2 from smaller than pi over 2. See? And what happened to the output? Okay. The output is getting higher, even higher yet. And as we're getting closer and closer to pi over 2, you can see the output is getting higher and higher yet. But of course, never touch the broken curve, but get infinitely close to it. So that's why we say that this is going to be, the infinite limit is going to be a positive infinity. Positive infinity. So from that picture itself, you can tell. Okay, so we can learn a lot about it. So you can think about, what if I approach pi over 2 from larger than pi over 2? Right? So that's going to be approaching negative infinity, right? Even though we didn't ask that question. All right, so let's get to number 13. We did number 12. We did number 12 earlier. Okay, so we're doing number 13. Okay, just assume we might need this. I think we will. Okay, so let's look at number 13. Number 13, I copied the question correctly. Yes, 14 and 15. So we have 3 more questions. So 13. In this case, we have 2. One is 1 over x. We cannot separate them. We cannot separate them, by the way, okay? So you have to consider them as a whole. As x approaching 0, from larger than 0, and for 1 over x is going to be approaching positive infinity. Well, but what happened to ln x? Ln x, as x approaching 0 from larger than 0, that's going to be approaching negative infinity, right? We're by this time, we're pretty familiar with it, right? We're pretty familiar with it. So a positive infinity subtract a negative infinity. Remember, a negative ln x approaches a negative infinity. So it's more like infinity minus negative infinity. So that's going to be positive infinity plus positive infinity. And of course, that's going to be a positive infinity. All right? Last but not, no, second to last. Tangent x, okay? We use tangent, we did work with tangent x, so we just bring this back. We just bring it back. But this time, of course, it's at different points. Okay, it's a negative pi over 2 from larger than, right? Negative pi over 2. So I'm going to draw the vertical asymptote again, right? So it's going to be, this is negative pi over 2, and there's another point, right? So it's negative pi over 2, right? when we approach negative pi over 2 from larger than negative pi over 2, okay, this is a positive sign. So we're approaching, make it thicker, right? We're approaching negative pi over 2 from larger than negative pi over 2. So that's how we approach negative pi over 2. The output, right? The output is going to be getting lower and lower and lower yet. You guys follow me? Okay. So of course, then this limit will be approaching negative infinity. Okay, so that's how we observe the picture. Observe the picture. Okay. One more question. One last one. One last one. Okay. Number 15. Number 15. Number 15, we have two quantities. Again, this time we cannot separate them because we just have to work with them. And especially when x approaching 0, I think I might have left. It's x squared. My bad. Okay, ln x squared. Okay, ln x squared. Otherwise, we'll have a problem, right? Otherwise, I did not make up the question. Okay, somebody else did. So when x approaching 0, right? X squared is approaching 0 from larger than 0. Okay? And to just rewrite this form, and x raised to the power negative 2 is equals to 1 over x squared. So ln x squared, because x squared approaching 0 from larger than 0, ln x squared is approaching what? It's approaching negative infinity. It's approaching negative infinity. Okay? How about 1 over x squared? Right? How about 1 over x squared? X squared is approaching 0 from larger than 0. So this applies, right? Because this will be x squared approaching positive infinity. So we have a negative infinity minus a positive infinity, something like that. And therefore, this limit is going to be a negative infinity. Okay? Do you guys follow me? I hope you do. And I hope this helps. And if you have any questions, please don't hesitate to reach out to me. And thank you for watching.